An exponential model works great for things that have no limit to how high they can grow. So if you leave money in a bank account forever and it's gaining interest forever, then theoretically there is no limit to how high the account can go to. So if your initial principal and your interest rate are going to be constant, then your initial principal at year 0, the principal is the initial principal, and then at year 1, it has grown to 1 plus your interest rate raised to the first times the principal, so you get that amount of interest. The next year, you get a little bit more interest because you get the same interest that you got the first year plus interest on this interest. So you're starting with interest on this amount. The third year, you're starting with this essentially as the principal in the account. So you get the interest on the original principal plus the first interest plus the second interest. So now your amount in the account is up to here. However, with populations, whether it's bacteria, deer, rabbits, fish, people, viruses, there is going to be some kind of ceiling to how high that population can grow. If you start with a sufficient population to create a certain growth rate in the population, it's going to increase much like this for the first few years. But when it starts to reach the point where there's only so much food and so much space and so much water, then it's going to reach the maximum population that the environment can hold. Now, of course, it can't start out actually at 0. So it's got to start out with some population. It wouldn't start at 0 or you wouldn't have any growth. But the logistic model here is based on these P's are not the principal, they are percents. So if you start out with just a tiny bit of population, let's say you start out at 2% of the population of the maximum population, then P of n that first year is going to be 0.02, so your rate of increase is going to be 0.98 of R. However, as your population percentage of the maximum population increases, when you get up to where you're at 98% of the maximum population that the environment can hold, then your growth rate becomes 1 minus 0.98, so now you're only growing at 2% of the population. And then that amount, whatever the percentage left to grow is, times your interest rate, that gets added to 1, and then that whole amount gets multiplied times P of n, similarly to your interest rate in an exponential model. So let's look at a problem here. Assume that a population is growing initially at a rate of 3% per year. So this is going to be R equals 0.03. Also assume that at the end of the 5th year, the population is 40% of its maximum size. So at the end of the 5th year, actually at P sub 5, technically, I can go ahead and put that in. That's where the n goes. P sub 5 just indicates the population rate, the population of the 5th year. It's 40% of its maximum size. So during the 5th year, it's at 40%. And we always put percents in as a decimal. At what percentage will the maximum size, at what new p-value, so p of n plus 1 is what we're looking for. We're looking for p of 6. Will the population be a year later? So p of 6, p sub 6, is going to be 1 plus 0.03 r times 1 minus the population percentage that you've already gained at the beginning of the year or at the end of the previous year. So that's going to be the 40%. And that's going to be multiplied by the 40%. So to do the math, you follow your order of operations, working from the inside parentheses first. So we've got 1 plus 0.03 times 1 minus 0.40 is 0.60. And I would suggest that you put this into your calculator one step at a time so that you can follow what's happening. Otherwise, if your answer's wrong, you will have no idea where it happened. And it would be so easy to put in a wrong parenthesis or something here. So the next step is to do the multiplication here. First thing we do is this. Next thing we do is going to be this. So we've got 1 plus that 0.0018 or 0.018. Of course, 1 plus 0.018 is going to be 1.018. This now gets multiplied times this. This is multiplied here. So it might be easier to tell if I put the parentheses. So this is going to be multiplied by 0.40. Which turns out to be 0.4072. Now they always round that up. .4072. Watch on your instructions and see how that says to round it up or to round it off at all. That is essentially 40.72%. So at the beginning of the year or the end of the previous year, it was at 40% of the maximum capacity for the population. And at the end of the 6th year, it's now, this was 40%. So at the end of the 6th year, it's now at 40.72%. So let's look at one more example. If the initial rate of the population growth is 4.5%, and the population percentage at the end of the 8th year has reached 72% of the maximum population, find what the percentage of the population of the maximum population will be at the end of the 9th year. And you actually have to do this year by year by year. So P of 9 is going to equal 1 plus 4.5% is the same thing as 0.045. 4% would be 0.04, so 4.5% would be 0.045 times 1 minus the end of the 8th year was 72%, so that's 0.72. And this is also going to be multiplied by 0.72. This is always the difference between that and 1, and this is always the original number. So if this is 0.72, this is going to be 0.28. The two of these will always add up to 1% or 100%, sorry. So we've got 1 plus 0.045 times 0.28. Multiply these out. That's going to be 0.045 times 0.28. So 0.0126. So this is going to be 1.0126. So basically, at the end of the next year, it's going to be at 100 and slightly over 101.25% of, or it will have increased by another close to 1.25% of the 72. So add 1 times 0.72. This comes out to 0.729072, which is going to be approximately 73%. So it's at 72%. A year later, it's at 73%. So it's increasing at this particular time by about 1% per year.